Good afternoon, students. Welcome back to our daily discussion. And for today's topic, we're going to discuss and explore elementary properties of groups. The book that we are going to use today, it's all about the fundamentals of abstract algebra book. So before we proceed to our discussion today, let me introduce first to those students who are not familiar with me. I am your teacher Ray, a second year student. I came from GHCC Domingue campus. If you have any queries, you can message me or email me. Account Raymond Bilchar, and for my email account alonhansom143@gmail.com. Without further ado, let's discuss our learning objectives for this afternoon. At the end of the lesson, the students are able to conceptualize the elementary properties of groups and proves theorems by using elementary properties of groups. Alright, let's start with definition 2.1.1, a group. Okay. Who wants to read? Okay, Charity. Alright, thank you. So, a group consists of ordered pair where G is non-empty set and star is a binary operation on G such that the following properties hold. Alright, before we are going to proceed with the properties, a group has a ordered pair. So that ordered pair is composed of a set and a binary operation. We don't know yet what operation will be. So in abstract algebra, we will be given an ordered pair like this one. Alright. So for G1, for all ABC is an element of G, where A star B star C equals the quantity of A star B star C. We know this property is associative, and a group holds associative law. For G2, there exists E is an element belongs to G such that for all A is an element G, where A is star E is equals to A equals E star A for the existence of an identity. For G3, for all A is an element of G, there exists B is an element of G such that A star B equals E equals B star A is the existence of an inverse. Theorem 2.1.2. Let G star be a group. Alright. Number 1, there exists a unique element of E belongs to G such that E star A is equals to A equals A star E. For all A is an element belongs to G, for all element of A belongs to G, there exists a unique B. Right? Unique element B belongs to G such that A star B is equals to E equals to B star A. Alright. For number 1, we prove that by G2, by using G2, there exists E, element of E belongs to G such that E star A equals A star E for all element of A belongs to G. Since G star is a mathematical system, then E is a unique by theorem 1.6.11. So the previous teacher discusses this. So we conclude that the unique element of E belongs to G satisfies G2 is called identity. Take note that where an identity operates an element or an element operates identity, then the element doesn't change at all. For example, in this case, we have here, our element is A. And then, our identity is E. We have star here. We're gonna put star. Okay. Where identity operates, or the element operates E, and then that would become A. Or, where the identity operates A equals to A again. It doesn't change at all. Take note, where an identity operates an element, or an element operates identity, then the element doesn't change at all. Alright. For number 2, our proof, let A belongs to G. By using G3, there exists B is an element of G such that A star B is equals to B star A. Suppose there exists C is an element that belongs to G such that A star C equals E equals C star A. We show that B equals C. Now, B equals B star E. Alright? We substitute our A star C to our E, this one. We substitute this one. This A star, oh my goodness. This A star C to our E. And then, we will have B star A star C. And by using associative law, we can move our parentheses. So that would be B star A. It states in our number 2 that B star A here is equals to E. And the E there is an identity. So when we operate E to our C, and then when we recall from number 1, the element doesn't change at all. So we will have C alone. So therefore, B equals C. Then let A is an element of G. Then the unique element B is an element of G that satisfies G3 is called inverse, which denotes A inverse. And thus B is unique. And B equals C. And B equals C is true. Alright. In continuous with the theorem that we have, if a group G star has the property that A star B equals B star A for all AB is an element of G, then G star is called commutative or abelian group. A group G star is called non-commutative if it's not commutative. Alright. In this example, consider Z, the set of integers, together with the binary operation plus, where plus is the usual addition. We know that plus is associative. Now, 0 is an element of Z, and for all element of A belongs to Z, where A plus 0 equals A equals 0 plus A, and so 0 is the identity. Also, for all A is an element belongs to Z, where negative A is an element of Z, and A plus negative A equals 0 equals negative A plus A, that is, negative A is the inverse of A. Hence, it now follows that the Z integer plus the binary operation is a group, since A plus B equals B plus A, for all AB is an element of Z. And then our binary operation, which is plus, or the addition, is called commutative. Thus, Z plus is a commutative group. Differentiating of abelian and non-abelian group examples. This one. I made this one to make it clear enough for us to understand the abelian from the non-abelian. For abelian group, if A star B is equals to B star A, for all AB is an element that belongs to G. For example of that, if we have 3 plus 4 equals 4 plus 3, and then we will have the same answer. That would be 7 equals 7. And for non-abelian group, it is opposite. So if A star B is not equal to B star A, for all AB is an element of G. For example, is that 3 minus 4 equals 4 minus 3. And then we have negative 1 is not equal to 1. So, non-abelian group can be called also as non-commutative group. And for the abelian group can be called as commutative group. One of the example of non-abelian group. is that the group of 2 by 2 matrices with non-zero determinant under matrix multiplication, we have there example 2.1.10, let GL2R equals the matrix ABCD such that ABCD is an element of all real numbers where AD minus BC is not equal to 0. We define a binary operation star on GL2R by ABCD, the matrix of ABCD, the binary operation, and then we have UVWS equals to AU plus BW, then AV plus BS, and then CU plus DW, and CV plus DS. So for example, we will have the matrices of 1, 1, 1, 0, star 2, 3, 0, negative 1, and then 2, 3, 0, negative 1, star 1, 1, 1, 0 equals. In this case, we need to show that this is non-commutative group. So, in this one, we times 1 times 2 plus 1 times 0, and then we will have the result 2. And 1 times 3 plus 1 times negative 1, and then we will have the result of 2. And the same with the other 2's in below. So recall, a commutative property where AB is equals to BA. Hence, GL2R star is a non-commutative group. So theorem 2.1.11, let G star be a group. For number 1, A inverse to its inverse is equals to A, for all A is an element of G. We prove that A inverse to the inverse equals to A. We show that A star A inverse is equals to the identity of its element. And then, we know also for the fact that the inverse of its inverse will come up with A. For example, if we're going to use numbers here, 3 to the power of negative 1 times to the power of negative 1, we know that 3 negative 1 is 1/3, right? 3 to negative 1 is 1/3, and times its exponent, we will have 3. So therefore, in this case, A is equals A is true. For number 2, where A star B inverse, where we can say that the inverse of A star B is equals to B inverse star A inverse, for all AB is an element of G. Sachs and Schuss theorem. Alright. When we put Sachs and Schuss theorem, we put first our Sachs and then Schuss. When we take off our shoes, we take off first our shoes and then our socks. And that's the theorem all about. So, prove the AB inverse equals B inverse A inverse. Consider that AB inverse is an element of G. So therefore, the inverse of AB inverse is equals to AB. We know that for sure B inverse A inverse is equals to AB. So, AB inverse times AB is equals to A. We need to show that this B inverse A inverse times AB is equals to A. Consider B inverse to A inverse times AB. By using associative property, we get the A inverse times A into identity. Alright? We could see that A inverse and A have the inverse property, and by multiplying A inverse and A, we will have identity property. And then, by associative property again, we multiply EB, and then we know that when the element operating to its identity, then the element doesn't change at all. So we will have a letter B. So B inverse times B, by using by inverse property, we will have E. So B inverse A inverse times AB is equals to E is true for this theorem. For cancellation law, for all ABC is an element of G if either A star C equals to B star C or C star A equals C star B, then A equals B. In this case, we're going to use left cancellation law. So we have two different types of cancellation law. And that would be the left cancellation law and right cancellation law. So if C star A equals C star B, then A equals B. Proof. Assume that C star A is equals to C star B. Show A equals B. Since C is an element of G, then C inverse is an element of G. So, we have there C inverse star C star A equals to C inverse star C star B. By associative property, we combine C inverse and C, both left and right. We have the inverse property. So, we will have then A star A equals to A star B. And then, by identity property, we will have A equals B. And then, the theorem is proved. And for the right cancellation law, they have the same concept, but this one is on the right. We put the inverse to the right. So, if A star C equals B star C, then A equals B. Proof, assume A star C equals to B star C, then we show A equals B. Since C is an element of G, and C inverse is an element of G also, so A star C inverse equals B star C star C sub C inverse. By associative property, we combine C and C inverse, and then we have the inverse, and then we get E. And by identity property, we multiply, or we operate A star E, and then we will have A and B star E, and we will have B. So A equals B. And the theorem is proved. For number 4, for all AB is an element of G, the equations A star X equals B and Y star A equals B have unique solutions in G for X and Y. Proof. Consider A star X equals B. Since AB is an element of G, then A inverse is an element of G also. The solution, A inverse star A star X equals A inverse star B. So by using left cancellation law and then associative property, we combine A inverse star A, and then we will have the inverse, and then we have the identity property, which is E star X, and then we will have X equals A inverse star B. So X equals A inverse star B exists. So, to show uniqueness, let X sub 1 and X sub 2 is an element of G such that A star X sub 1 equals B and A stars X sub 2 equals B. By transitivity property, A star X sub 1 is equals to A star X sub 2. Since A is an element of G and A inverse is an element of G also, then we just going to substitute the first one. Alright? So A inverse star A star X sub 1 is equals to A inverse star A star X sub 2. By using left cancellation law, by associative property, we combine A inverse and A, and then we have E. Associative property. And then, getting in the inverse property, we have E star X sub 1 equals E star X sub 2, and by identity property, we have X sub 1 equals X sub 2. Therefore, X sub 1 equals X sub 2, meaning the solution exists and unique. And it is already proven. So it holds the same argument for the equation Y star A equals B. For corollary 12.1.12, let G star be a group and AL is an element that belongs to G. If A star A equals to A, then A equals to E. If A star A is equals to A, then A equals E. Proof. Assume that A is an element of G, where A inverse is an element of G. Since A star A is equals to A, by cancellation law, you can use left cancellation law or right cancellation law. By using left cancellation law, we will have A inverse star A equals A inverse star A. By associative property, we combine A inverse star A and then A inverse star A from the right. We then get the inverse property. And then, by getting the inverse property, we will have A star A equals to E. And the only remaining here is that from the left, we have E star A, and by identity property, we have A equals E, and thus, the corollary is already proven. Corollary 2.1.13, in a multiplication table for a group G star, each element appears exactly once in each row and exactly once in each column. So we have here, we assume that the G star, where the binary operation is defined as like this: star E A ellipsis to N. And from here down there, we have the same as here down there, right there. All right, the property said each element appears exactly once in each row and exactly once in each column, which is true. So we have here, this is the E and the E and the A and the A, and so on and so forth, and N. And that is true. And this table can be called as the binary operation table. This one, referring to this table. All right. I want a volunteer to read for the corollary again. Nika, thank you. Thank you. In this case, students, we have two solutions. All right. The first one is no element can show up twice in any row or column. We assume that there exists B is an element of G such that B shows up twice in a row. Then there exists UV is an element of G with U is not equals to V such that B equals to A star U and B equals A star V. By transitivity property, A star U is equals to A star V. Using left cancellation law, A inverse star A star U equals A inverse star A star V. By associative property, we combine A inverse star A from the left and we combine also A inverse star A from the right. And then getting the inverse property, we will have A star U equals to A star V. By identity property, we will then have a U equals V. Thus, the equation A star X equals B has two distinct solutions, U and V. This is a contradiction to Theorem 2.11 since the equations A star X equals B has a unique solution for X. A similar argument for columns can be used. And for the second way, every element appears at least once in every row and column. So let G star be a group and ABC is an element of G. Then by the associative law, A star B star C equals A star B star C. Hence we can define A star B star C equals to A star B star C equals to A star B star C. As you could notice, by using associative law, we can transfer our parentheses to element to element. Then, let A, B, C, D is an element of G, then A star B star C is an star D equals to A star B star C star D equals to A star B star C star D is equals to A star B star C star D equals to A star B star C star D equals to A star B star C star D. Thus, there is more than one way of inserting parentheses in the expression A star B star C star D to produce a meaningful product of A, B, C, D in this order. We now extend this notion to any finite number of elements. So, G is a group with n elements. This implies that each spot in our operation table has n options. We can't have more n options since we know it must be close to under operation, meaning no element on our table can be an element that's outside of our set G. So this is the end of part 1. But students, before I'm going to say goodbye to you for this discussion, we will have a quiz. So let G star be a group, AB is an element of G, and MN is an element of Z. Prove that 1 to 5. Alright, please take a screenshot. Are you done? Thank you. And for our assignment, can you read Miss Kulot for the assignment? Yes, yeah. the continuous of that part is in additive notation. Rewrite the statements and proof theorem. This chapter 1 in additive notation. Thank you, Miss Colette, for reading that one. So that's all for this afternoon class, and I hope and pray that you do your best for answering your quiz and your assignment. Thank you and God bless.